I'm going to talk to you about unmanned underwater vehicles and some of the challenges and applications of these. Most people don't know that Boeing does underwater vehicles. We're one of the few companies in the world that does everything from the deep sea all the way out into outer space. We actually started back in 1965 when it was a 50-year history doing subsea work. A lot of it was research and development with various hydrodynamic shapes, which you see at the very top. We even had a manned vehicle called Beaver, which was for exploration in oil and gas, down to various other military applications and targets for submarines and countermeasures and mine hunters, which is one of the leading applications of the military, searching for underwater mines. Down to the bottom here where we have a large survey vehicle and the long-term mine reconnaissance system. What you see down here is the Wrigley Marine Science Center. That was originally established by our company, and now it's part of USC. And we regularly go out there and do operations out of that facility. I'll discuss some of those ones we did this year, in fact. So all of you are all ocean enthusiasts, so the materials you see up here, you've seen before. 72% of the Earth's surface is the ocean, 1.3 billion cubic kilometers. To put that in context, if I could survey 1 cubic kilometer per hour, it would only take me 150,000 years to cover all the ocean. The average depth is greater than 3,000 meters. That's an important factor that we'll talk about a little bit later. That's really one of the big challenges in going out there and finding what's living and what the ecosystem is like and its contribution to climate and weather. Deep ocean currents are just starting to get a lot of research. And then approximately half of that ocean is greater than that 3,000 meters that I said there. So most of the ocean is incredibly deep. 3,000 meters, 10,000 feet, roughly 2 miles. So some of the challenges we face, and this is just in general in going underwater, but especially with my technology of unmanned underwater vehicles. Communications. Communications is very limited underwater. We're actually limited to acoustic communications, which has the speed of an old dial-up modem. That's why I put the picture there. So you think about what it was like to use a dial-up modem and just download a picture of your kids or something, and it would take you 5-10 minutes. Well, that's the problem we have in the state of the art today. That's a limit of physics more than anything, but there's some new technologies I'll talk about later. Another really big problem, unlike aircraft, and you see all this stuff about unmanned drones flying around, they have access to GPS. We have no access to GPS. When we're underwater, we're on our own. We have to really pay a lot of attention to our navigation. So we invest very heavily in technologies and capabilities in refining that, especially when you talk about long distances. In addition, there's no light. The deeper you get, the darker it gets, which it makes a challenge for seeing anything. So usually one of the sensors of preference is using sonar. Been used for many years, but there's been a lot of technology advances that give us even 3D sonars these days. And then energy. Energy is the other big deal. Energy dictates how long I can stay out, how much I can do when I'm underwater. The more energy you have, the more you can do, the longer you can stay, the bigger area you can go to. For example, all of you have seen that the unfortunate MH370 missing airliner, they brought in an AUV to start searching for that. That AUV can probably only go for 24 to 48 hours at a time, and you're trying to search 100,000 square kilometers. So it will take them, to cover all that, it could take them a couple of years. One of the reasons is because I have to keep bringing it back up and I have to keep recharging. If you could have some persistence, like a nuclear submarine, let's say, then that job would be a lot easier. But we can't put nuclear power on an unmanned system, and it's not a good idea. So another big challenge we have, pressure. I talked about the 3,000 meters, places where it actually goes down to 7 miles depth, where James Cameron took under the trench. So this is the average, this is just a stick figure of a person. The average person is about 2,600 square inches. So this is a standard SUV. It's about 4,500 pounds. So when you're about 3,000 meters, you experience about 4,500 pounds per square inch. So if you're at 3,000 meters, you're feeling the weight of 2,600 SUVs on you. You go down to 6,000 meters, and it's twice that number. So this is a big challenge. That's one of the reasons the technology is not very inexpensive. It's very expensive. And one of the challenges to operate down there. And if anything goes wrong, obviously, it's pretty catastrophic. So we do all types of different things to mitigate these things. How we typically do it is we will use a series of pressure vessels in the vehicle, and I'll show you what a layout of one of our vehicles looks like. Instead of a single hull like a submarine, this allows us to package different components discreetly and manage the pressure a lot better. And the bigger the pressure vessel gets, the thicker it gets. And if I try to make one large one, I could have titanium or steel or aluminum that's a couple of feet thick just to start going down to some of these depths. So what is an AUV? Maybe I should have started with this one, but we'll lead up. We led up to it now. There's two types of technologies, robots that are used offshore and in the deep water. One's a remotely operated vehicle, which you're used to seeing, and one is an autonomous underwater vehicle, or in some circles, an unmanned underwater vehicle, or UUV. Remotely operated vehicles you see a lot when you watch the documentaries on exploring the Titanic. These are tethered vehicles. They usually have a fiber optic communications link, so they can give you real-time information back up to the surface. They have power coming down the cable, so they pretty much have unlimited power from the surface vessel. And all of their capabilities are really driven by the human behind the controls. The human can actively control it, can take in all the sensor inputs and make decisions just like you and I do when we're driving a car. The big challenge with the AUV is it's tetherless. Now, you can't communicate with it easily. I mentioned the dial-up modem. I can't take a joystick and control an AUV around, so it's got to be a lot smarter. It also has self-contained power. I no longer have that plug back up to the surface, so I'm limited on how much power I can take with me. And I'm again limited because I have to put that AUV on the back of a boat, and the boat can only be so big. So that limits the size of the AUV that you can reasonably and safely handle on and off the boat. And that, in fact, plays into the amount of energy you can store there. And I mentioned autonomy. Because we're tetherless, we have autonomy. Autonomy is a pretty broad term. It's very similar to artificial intelligence. It comes in many flavors. But really what it is like I mentioned, you drive in a car, you get inputs of sound, you get inputs of sight, and your brain magically incorporates those into decisions. Well, we have to program these robots to take in all of these different pieces of information. They can be sonars that are looking forward, looking for obstacles. They can be sonars looking down to make sure you don't hit the ground. They can be cameras. They can be just about anything you think of. And we're going to take all that data and we are going to process it and put it into our computer brain and make a decision to make sure that we don't run into the ground or hit a boat or run into a sea mountain or even run into a biologic. It's a very, very challenging technology. Now, the levels of autonomy range from things that are very simple. There's some very simple robots out there. Literally, you can turn a knob on the side and you'll set how fast it goes. And you'll turn another knob on the side and it'll tell you what bearing it'll go. And then you turn another knob and it'll do turns at the end, and you throw it in the water and it just goes off for 15 minutes and does that. All the way up to, I put the vehicle down and I leave it there and there's no boat communicating with it. And it goes into box canyons that you've never seen before. Most people and myself included before I started working in this industry, is you look at something like Google Maps or even the old National Geographic maps you used to put on the wall. You see all these great topologies of the ocean bottom and all the bathymetry. You think, wow, we got the whole ocean mapped. Well, we don't. It doesn't look anything like that. All of that stuff is done from the surface. And it's just like with optics and things like that. Range is, the resolution is a function of that range, and also frequencies and sonars. So you can be in very deep areas where these sonar bathymetry images you're taking can be 30 square meters in resolution. So I go back to the MH370. We have a very large aircraft. Well, 30 square meters is over 100 feet by 100 feet. You can quickly get into a place where if you did have an airplane, it would just show up as a pixel. You no longer can distinguish any of its features. So most of the maps you see show gross features. When you actually go down there in some of those very flat places, we found that they are not so flat and they're not so benign. That goes back to the autonomy. You have to put this vehicle out there in an unknown place with no really high quality maps and make sure that it doesn't run into things, it doesn't get stuck. It's got to protect itself. It's out in the wild world. Then there's medium range autonomy, which the vehicle has a lot of intelligence, but usually a surface craft will sit over top of it and provide it with position fixes and monitor to see if there's anything wrong, and can even change its course and direction if need be. But usually they do everything on their own. So I don't get those down in the bottom of the ocean. So classes of AUVs. I point out a specific one here as a glider because I find it interesting. So there's man-portable, and they can be gliders, but these can be simple little AUVs, have a propeller, have control surfaces, have a limited amount of autonomy. They can run for a few hours. They can run specialized sonars and cameras. You see a lot of them. The Navy's used them for mine hunting. They've a lot of the research groups use them because they're inexpensive and they provide a unique capability. There's lots of very great products there. The glider, the reason I point that out, this one's really interesting. It doesn't have a propeller. It powers itself by changing its buoyancy. So literally, you put this glider, and you can see this path down here. That's the path of a glider. They can stay out for months and months at a time. And all they simply do is get heavier and, well, that's incorrect. They don't get heavier and lighter. They change their actual displacement. So basically, effectively changing their density. And that allows them to go heavy or light. And you can change your displacement by there's a number of methods, but one method we've used in the past is you can have a hard, like gas tank, and then you can have a soft bladder tank. And I can put a liquid inside that hard tank, and when I pump that liquid out into these bladders, it changes the volume that I take up, therefore changing my displacement. My weight hasn't changed, but I displace more water, and therefore I have different characteristics. Lightweight vehicles are in the 500-pound range. They're a little too heavy for a couple of people to operate. They're about 12.5 inches in diameter. They have endurance of a few hours as well. This could be anywhere from 2 to 12 hours. Heavyweight vehicles, basically that's the size of a torpedo. About 3,000 pounds, so about the weight of a normal car. 21 inches in diameter, and those ones can actually have endurance anywhere from 12 hours to maybe close to actually 2 days, depending on what kind of battery and power source you're using. And then there's the large displacement vehicles. They're in the tens of thousands of pounds, greater than 36 inches, and they can have endurance definitely in the multiple days range. We happen to specialize more in the large displacement vehicles than anything. Applications. So standard applications today is usually surveying the bottom. It's looking for items on the bottom, a shipwreck, or Amelia Earhart. It does search and terrain. Oil and gas uses them to do a survey if they're going to lay a pipeline to make sure they're not going across some sort of habitat or some sort of rock formation or something that's going to cause damage. The critical infrastructure protection, so harbors, offshore critical infrastructure, there's power lines running from different places, there's telecommunications lines, there's pipelines. Environmental survey. This is something I'll even touch on, a particular mission we did earlier this year. While you're out there, you can collect all kinds of information on the characteristics of the ocean. You can use mass spectrometers now. They have them small enough, they fit in these vehicles. They can go to 6,000 feet, and they can collect all of this information just nonstop as you're running around. Or you can go take samples of very specific items. We can constantly measure the salinity as we change layers in different locations, the temperature of the water. There's fluorometers, there's all kinds of things that can assess biologic presence, hydrocarbon presence. These are great technologies that you really can't get to readily, and these vehicles can go and search an area and collect a large amount of correlated data in these areas. And what I mean by that is in a lot of surface vessel operations, I take a measurement with the device off the side and I collect that data. And then I take another measurement from another device. And this could be over days. Well, an AUV can go and have all those sensors running simultaneously and cover a large area, and all that data is collected at the same time. This is great for scientific purposes because any samples over time can introduce some uncertainty in the modeling. Fish assessments. This is a new one. We just did this earlier this year, and I'll cover that. Some of the sensors of choice, you'll see the text is kind of small. Side scan sonars. These are high resolution sonars that literally look down the side as you fly along and cover 2 areas to each side. Synthetic aperture sonars. Synthetic aperture sonars are a variation on this where they use a processing technique and some other different characteristics of sonar to make very high resolution sonar images. And when I say very high resolution, 10 centimeters. In sonar terms, that's really good. Multi-beam sonars are typically like the ones that made those bathymetry maps of the ocean bottom I'm talking about. They're very simple, but they're very accurate at measuring bathymetry. They can pick up very good features. Their resolution is really a function of their depth there. And a lot of times multi-beams can be used in a variety of ways. They can be used for fish counters. They can be used for bathymetry, and they can also be used for situational awareness. They can be your eyeballs. Obstacle avoidance sonar is a little simpler version of the forward-looking sonar, and then a sub-bottom profiler literally can go and can map out the seafloor and to extend a couple meters underneath the seafloor to see, you can get an idea of what stratification is there, what types of different materials is in the soil. Is it all mud? Is it all sand? Is it layered? Is it a hard bottom? All very common things. So this brings us to Echo Ranger. So the way I got invited here is we had just completed a mission with NOAA using Echo Ranger. First of its kind with Echo Ranger, and the first of its kind with Southwest Fisheries out of San Diego. What we did is we took Echo Ranger, which is a large vehicle here. It's about 18 feet long. It's about 3.5 to 4 feet side by side. It's a square vehicle. It goes to a maximum depth of 10,000 feet, 3,000 meters. It is totally autonomous. It doesn't require a surface vessel over it, but it doesn't hurt to have one. Make sure you know where it is. It has a very large payload bay. And payload is just a generic term of anywhere I can stuff a sensor. And we can provide a lot of power, processing, and smarts to these payloads so that we can do a variety of missions. And what you see, and I have a better one that has a cutaway here, right there. So I mentioned, how we separate things out. So you saw that yellow skin. This vehicle is really a flooded vehicle. All of this area in between these pressure housings is just water and foam. We use the foam to manage the buoyancy there. We have active ballast tanks, which take seawater in and out to change our actual weights. This is the main pressure vessel, which houses all the brains and all the batteries. And actually, most of this is batteries to get the kind of density and the duration we're looking at. Echo Ranger can go for a couple of days underwater unaided. What you're seeing here is the original application of Echo Ranger was oil and gas surveys that I mentioned. And one really interesting thing to note on the autonomy is it's a little hard to see up here. You see this picture up here, this blue track. This is the data off the vehicle after doing a survey. We run it through, we make sure everything went well. And when we did the analysis, we see this circle here. Well, what happened there is the vehicle was doing its survey, and all of a sudden it had a failure in its payload. And when a failure happens, the vehicle's smart enough to say, oh, I gotta stop. I gotta try to fix this. And the vehicle will fix the problem. It'll try to reboot the payload, it'll try some reconfigurations, until a point where it will say, I either got it back online and I continue exactly where I left off, or it will say, instead of, in the case of a side scan sonar where I have two lobes, if I only have one, I will replan my survey to take into account that I only have half of my sensor. And I will go do as much of that survey as I was told to go do, and then head home. This one is interesting here, this circle. This is actual side scan sonar data. I told you it's high resolution. It's not high resolution like we're used to with visual stuff, but for sonar, that's really good. What this is we have an oil platform here. And it actually has concatenary cables that are coming out to keep it in place. And we programmed Echo Ranger to go and do a survey through all those cables and all the supports. And again, that blue area up there is the post-survey data that shows you the concentric circle we did in through that maze of underwater obstacles. So NOAA, we did a rockfish survey with them. NOAA does all the fishing assessments, fish stock assessments. This goes into fishing limits and obviously environmental and habitat health analysis. They have some challenges when they go into certain habitats, and particularly rockfish. Rockfish, well, they live in rocks, and they have a hard time getting into the rocks. They try to use ROVs, and they do a pretty good job of that. But if they want to do a fish sample in a lot of areas, they'll trawl some of the fish, which is not possible in an area that's just a rocky mountain. So we got together and we said, well, let's do a pilot project. So we took their actual acoustic sensor they use, that's their standard scientific sensor to count fish. We took their stereo camera system, which they use to image the fish for species identification. And it's a stereo camera, the other side effect is they can get an assessment of size. And then conductivity, temperature, and depth. That measures certain properties of the water. Conductivity is really a slick name for basically salinity in this case. We integrated all of these into Echo Ranger and set out to go do a rockfish assessment right here off the coast. So this is what we did. We went to Wrigley Marine Science Center, and we would launch from their pier there, and we would have Echo Ranger programmed to swim up to the northwest corner there, where you see these areas over here are the areas of interest. And one of the reasons this place is great is they've already done surveys in this area in the past, so they have scientific data to go and measure, hey, this is how good it was last time, and here's how good it was to date, and here's the advantage or disadvantage of an AUV. In this case, it was an advantage, and to survey these areas. So we spent 3 days going through that area where the vehicle would transit up and would do searches in these areas very close to the edge of the island into very, 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 very steep rocky habitats. So here's some of the data that NOAA shared with us. And right here you see some of the bathymetry and map data, and some of the star areas. These are areas of interest where fish counts have been collected in the past. And then what you see here is an overlay of that area, and here's Echo Ranger's track, and these lines are the echograms that they get together, that they collected looking for the fish. And these black areas, where when the scientists looked at the data afterwards, determined there were locations of aggregate fish that we wanted to go look at in subsequent surveys. And these are zoomed in portions of this data, and this red line, that's the bottom, and then these big spikes show you where they found the fish. And why this is important is they have a sonar measurement of fish, and then down here we have the stereo camera. And now I can say this fish and this sonar information together, I can now identify fish without having to visually look at them all the time. I have an estimate of population, and I have an estimate of size, and all those unique things, which is a big advantage for them because they don't have to disturb the habitat as much, and they can do it more efficiently. Some more images of the sonar imagery from Gulf of Mexico. As you can see, this is what a side scan image looks like, and this is the seam where they cross tracks. This is some of the bathymetric data I'm talking about. In a lot of cases, we get a map, and like I said, it's very smooth, and this is what the vehicle comes back with and shows us what it's really like. We're looking at a resolution of inches to feet, where I had mentioned before, other sonars will be in the tens of meters. So this is one of my favorites because, well, I was in charge of the later portions of this. This is called the ANBLQ11 system. It's a crazy Navy name, who knows what it means. But the other term was the LMRS system, or Long-Term Mine Reconnaissance System. The main purpose of this system was to launch an AUV from Los Angeles class submarine, and it would go into an area and do a detailed survey looking for mines. And that wasn't the real unique part, because a lot of AUVs have done portions of that in the past. The real unique part is this vehicle would come back to a predetermined location, at which point the submarine would meet up with it. And we would have a large fixture that came out of the upper torpedo tubes. So this is a real submarine, our vehicle, and our recovery arm. The vehicle, on command, would start to track the submarine and line up with it. And then the operator would give it another command, and the vehicle would line up behind this recovery arm and then begin to swim up this we had a very high frequency sonar signal that the two platforms could exchange data and home in on, and eventually dock with this recovery arm. The recovery arm would then manipulate the whole vehicle back into the lower torpedo tube, pull it back in. And this is all done while the submarine is submerged and underway. So let's, one of my favorite things here. So a little video. Okay, well, initially here, this is just kind of an artist's rendition of what to give you an idea of what is going on here. So that's the vehicle's when it's docked, that's the recovery arm, and it's gonna take control of the vehicle, it's gonna manipulate it into the lower tube, push it back where there's a winch that grabs the tail and pulls it right back in. Easy, right? So this is the actual test. It's hard to see, but this is a submarine right here. And this is the vehicle flying up in its approach to hit that roughly 1 foot cone. And it gets a toe position because that body is going like this. So it comes back, grabs the back end of the vehicle, and then aligns it to the lower tube. And so that's the hull of the submarine, that's the upper tube and the lower tube. and the tail of the vehicle. This is the camera view from the winch. We put a nice little camera in there to see what was going on. And then the recovery arm lets go, pulls the vehicle back. Its docking stab retracts, and they pull it back into the torpedo room. Now, all of that was done down in my horrible time in the Bahamas. And we successfully did it twice. We had impulse launched the system over 17 times. To even be able to get on a submarine, we had an even harder challenge. We had to prove that we could reliably dock this vehicle with a cone and a moving target. And why is it even more challenging? I had to do it from a surface ship. And doing it from a surface ship turns out to be a lot harder. Because acoustically, I have all of this noise from the waves and the wind and this big barge we're pushing through the water that's tied to two 10,000 horsepower tugboats. But we still were able to prove that this vehicle could do it. And the vehicle did it at about a 97% success rate against a surface craft. So that was more than enough to say, we're ready for the real deal. Once you're 200 feet underwater, it's real quiet. And a submarine is real quiet. So docking there was a piece of cake. It's the recovery part that got us all a little nervous. But we did it, and we did it successfully. So the future. I believe the future for AUVs, and this is me, Fred, personally, not necessarily the Boeing company in this case. I believe the future is very bright. These vehicles are just starting to make headway. They eventually, I believe, will be able to provide much greater utility in the bottom of the ocean and in the ocean. Not only for exploration, not only for environmental collection, but also for actually doing things like running equipment under the seafloor. You see all these big rigs, and you see some of them off the coast for oil platforms. Someday we may never have to have those. We can put all the equipment deep on the seafloor, and we can have robots like this come in and service that equipment. Whether it's replace parts, whether it's inspect parts, it's sampling, there's no end to what you could think that these can go do. They can deliver equipment to the seafloor. Technically, there is no limit on how big these could be, unless you're tied to a boat. But what if you aren't? What if you actually just made an unmanned submarine? Just like a big nuclear submarine now. Not necessarily advocating a nuclear engine, but there really is no reason you can't do that. And I think that someday we will see something like that. You'll still see the small vehicles. You'll still see ROVs. Those are all still needed things. Some of the enablers to that will be things like fuel cells. Fuel cells are starting to show up in cars. They've been working on fuel cells for I don't know how many decades, but really now they're really becoming viable. We personally do a lot of fuel cell work and work with a lot of people who've done fuel cell work. These will enable a vehicle to go a lot longer underwater. The reason being is you carry your fuel, and that fuel no longer requires oxygen because you carry your own oxidizer, your own oxygen in there. So I can generate my own electricity underwater. Where right now I have to charge up a battery, and I'm limited to how much I can draw off. Another real key innovation that's already been developed but is still kind of early is using visible light underwater. Underwater, acoustics really is king because it can travel very large distances, but it has very limited bandwidth. RF, just like radio or Wi-Fi, things like that can only be used when they're really close to each other underwater. You can get very high data rates, but you basically almost have to be touching in some cases. But LED comms and laser comms are two ways where we can get megabits, gigabits of information transferred between two platforms underwater through the water. The range is still not enormous, not as big as acoustics. I mean, acoustics can travel hundreds of miles depending on the frequency and what stratum of the ocean you're working in. But laser comms and LED comms have been proven at hundreds of meters range subsea. This is a big deal. ROVs have such a great hold on the undersea manipulation and operation market is because I can see it. I got a human, and if anything goes wrong, I got a human brain behind it. Well, what if I could provide a AUV that goes out into the oil field and then can turn on its communications link, and then a human can take over, and now it's a tetherless ROV that can get itself to the location and back. That's a powerful thing. So these are enabling things that will bring applications well beyond what we see today. Most of the applications, AUVs and UUVs, are primarily military purpose throughout the world. The second biggest is oil and gas, which is growing fast because AUVs have a certain amount of efficiency for doing surveys and application deep in the ocean. But exploration will also be greater if we get to these new technologies. It may not bring down the cost of the AUV, but it'll bring down the cost of operating an AUV. And you can also get to a point where you may be able to collect data while you're doing work for somebody else. These are all very, very amazing things that I think are going to come with this technology, and they will eventually shape the way things happen off the coast, and they will greatly impact organizations like NOAA and other climate scientists, environmentalists, and biologists. So with that, that's what I got.